The standard differential and integral calculus is based on being linear or additive, right? We have linear differential operators, things based in terms of infinite series, the integral itself being defined as a limit of a Riemann sum. But what if we could take these and turn them to be multiplicative, like having a multiplicative rate of change or a continuous product instead of a continuous sum? The most interesting thing to look at first would probably be a multiplicative type of integral. Now, based on the rules of logarithms and exponents, we know that the logarithm of a product is equal to the sum of the logarithms. Now, if we just exponentiate both sides, this is going to cancel out, and what we're going to get is that this product itself can be defined in terms of this sum, e to the sum of the logarithms, right? What if we consider these product or sums themselves literally being multiplicative or additive operators? So in this sense, what if we just define the multiplicative integral to be based on this formulation, right? If we have this multiplicative integral, or what's known as the geometric integral of f of x dx to be equal to e to the standard integral of ln of f of x dx, right? Now you're going to see a little bit after, based on the Riemann product definition, why we have this as an exponent here instead of like just standard multiplication in front. But basically, this is what we can start off with for the definition of the multiplicative integral, right? Now with this, because there is the logarithm here, technically f of x here should be a positive function or a function taking on positive outputs, right? Again, the logarithm of negatives can work out, but you know that's all complex and you have to work with different branches. So basically this restriction should stay. Now what we'll see here is that for the summation case, the Riemann sum, right, what we're going to have is we have the limit as n approaches infinity of, you know, the sum I is equal from 1 to n of f of xi times delta x. But then for this sort of Riemann product for our geometric or multiplicative integral, what we'll have instead is this limit as n goes towards infinity of the product I is equal from 1 to n of f of xi to the power of delta x, right? So this is basically where this power thing over here from the standard notation comes from, right? Now with this, because it's multiplicative, we have multiplicative rules, okay? Alright, so now basically things with products or quotients will become much more simple. For example, we have the multiplicative integral of f of x to the power of n, right? You can just take the power out like a standard product where you have just this, right? The power, you can take that outside. And then again, because this is multiplicative, if we have a product of functions f and g, if we integrate that, what we're going to get is just the separate product of the integrals. Right? Now, of course, because this thing is multiplicative, things like sums won't be as nice. Sums or differences make it much more difficult. Yeah, similarly with quotients, what we'll just have is that we're going to divide them out. So we're just going to have this f of x to the dx over multiplicative integral of g of x to the dx, right? And then also again, we were considering the indefinite integral here, but again, you just attach limits with the standard definition, and it's still going to be the same thing, right? If we have a definite multiplicative integral of f of x dx, say from a to b, then this is going to be equal to the integral from a to c of f of x dx times the integral from c to b of f of x dx for any a less than or equal to c is less than or equal to b, right? Normally with the standard integral you would split this up as a sum. Here we split it up as a product. Now we can also go over some example functions applying these rules or the standard definition, right? Say ourselves here we have the integral of a to the dx, right? So what is this going to be? Well, we're just going to apply the definition here. We have e to the integral ln a dx. This is just equal to e to the x ln a plus c. Now here, this stuff is just going to cancel out here. And again, now you see here, instead of having added on constants, we're going to have multiplied constants in front because of this e to the c part. You just take it out like you've seen in differential equations. What we're going to get is c times a to the x, right? So all indefinite multiplicative integrals will have a constant multiple here. Similarly, let's look at the multiplicative integral of x squared dx. This is going to be equal, so now we can take the power out. It's going to be equal to multiplicative integral x dx squared, which is equal to e to the 2 times integral of ln x dx, right? This is going to be equal to e to the 2x ln x minus 2x plus c. As you know, this is standard integration by parts. And so then with this part, what we're going to see is, so this cancels out over here, and here we're just left with another e to the x on the bottom. So what we're going to get in total is c times x over e, all raised to the 2x, right? Now we could also try to invert this for finding basically a multiplicative derivative, or we want to see if we can get something that we can apply a sort of multiplicative fundamental theorem of calculus. So basically, if we have this integral being defined like this, where we have this exponent on the outside and then the logarithm on the inside, well then, if we want to cancel with this logarithm on the inside, then what we would need to choose is some exponential, like some exponential involving an expression with f of x, right? So that's going to cancel with the logarithm on the inside, but then we also want to cancel with the exponential on the outside. So what would that have to be? That would mean that the result would have to be e to the ln f of x, right? So then why don't we just choose this thing to be e to the logarithmic derivative of f of x, or basically e to the f prime of x over f of x, right? And so this is the multiplicative derivative that we're looking for, which will basically undo this, and then we'll get basically a fundamental theorem of multiplicative calculus. This is going to be the multiplicative integral of the multiplicative derivative, or the geometric derivative of x dx to be equal to, oh yeah, we have to have the limits here, a and b, f of b over f of a, right? Basically, you can see that many of these formulas, we try to take a multiplicative form of the arithmetic, right? Like we have sums turning into multiplication, differences turning into quotients, right? So this is our fundamental theorem of multiplicative calculus. And also similarly with this, we can find a multiplicative form of integration by parts. We have the multiplicative integral from a to b of multiplicative derivative of f to the power g of x dx. This is equal to f at b to the power of g at b over f at a to the power of g at a times 1 over the multiplicative integral from a to b of f of x power of g prime standard derivative of x dx, right? So this would be the multiplicative form of integration by parts. Alright, so now focusing on the multiplicative derivative, f star of x, this is equal to e times the standard derivative of ln f of x, logarithmic derivative, or just e to the power of f prime of x over f of x, right? This is what we have. Unlike with the multiplicative integral here, transforming this into the nth derivative case is a little bit simpler. What we'll get here is just, if you want the nth multiplicative derivative of x, you can just take it to be the standard e to the standard nth derivative of ln f of x, right? I mean, again, anyways, the normal nth derivative is usually not that nice to calculate, but yeah. Also, with this, there is a nice connection to basically finance or economics. If we just take this as a type of interest scenario to derive the limit form by intuition of the geometric or multiplicative derivative. All right. So basically, if we have a case where we take we deposit $8 at the start of the year, and then after that year we're going to get $B, right? And so we know that the change is equal to B over A times, because if we want to get the total, right, we would multiply these together. A times B over A, this would cancel, and that would give us the B, right? That would be the result. That's what we want. Now if we did this for 12 months, every month, it would be a year total, still 12 months. We would split it and we would get $B. Now what we would have here is that B is equal to A times this change 12 times, which means that the change itself is B over A to the 1 over 12. Now if we take this and basically drag it thin to do it at like instantaneously every moment, what we're going to get is basically this limit. As h approaches 0, f of x plus h over f of x, all of this to the power of 1 over h, right? And this is basically the limit formula, limit definition of the multiplicative derivative. And it makes sense by this idea of taking this change in the deposit, which we'll just say the function for that is f, right? If we take this change in the deposit, the result at the end, if it's instantaneous, is going to be this small deviation, right? This small deviation with f of x plus h over the original f of x, right? And then to the 1 over h, that would be just the time interval, but here we're squeezing it thin basically, so that's going to be approaching 0, and that's where you get this limit definition for it. Now again, just like for the multiplicative integral, there are some differences with the rules that play more towards multiplicative arithmetic. For standard derivatives, added constants don't matter, but here multiplied constants don't matter. So if we have c times f of x, we take the multiplicative derivative. If we take the multiplicative derivative, it's just the same as ignoring that constant. Along with this, as you know, the product, you can just split this up as a product of multiplicative derivatives. And again, with a quotient, you can also split that up. So you have multiplicative derivative of f divided by multiplicative derivative of g. Now, we're going to need to use some chain rule usage here, and it's going to play a little bit between the different types of derivatives. But say if we have f to the power of g of x, we take the multiplicative derivative of that, what we're going to get is the multiplicative derivative of f to the power of g of x times f of x to the g prime of x. This is standard derivative here. And again, if you want a composition of functions for this form of the chain rule, then what you're going to get is the multiplicative derivative of f at g of x and then to the power of g prime of x, right? And again, because this is multiplicative, basically a rule of sums can be found, but it's like rather complicated and much more annoying now. If you want to take the multiplicative derivative of f plus g of x, this is going to be equal to the multiplicative derivative of f at f of x over f plus g of x times the multiplicative derivative of g of x at g of x over f plus g of x, right? So this is much more bulky than some of the other ones that were now simplified. And here I'm also going to show you on screen real quick. Instead of having tangent lines like we did for standard differential calculus, we can use this multiplicative derivative, or also a modified bigeometric form, to find instead tangent exponential curves or tangent power curves, because basically here these are our unit type of functions where if we take the multiplicative derivative for them, we're going to get constants, right? So basically that's what follows from this. There's the formula over there. But yeah, now we can go on to a couple of examples. Let's say we want to take the multiplicative derivative of x. So this is just going to be equal to e to the derivative of ln x, which is equal to e to the 1 over x, right? If we want to, let's take a look at the multiplicative derivative of ln x. So we'll have e to the d over dx of ln x, right? So this is just going to be, again, by the chain rule, we have 1 over ln x, and then the standard derivative of ln x is 1 over x, so we have e to the 1 over x ln x. All right. And now, with this, similarly to the standard form in differential calculus, there is a multiplicative form of the mean value theorem. We say if f is continuous and multiplicatively differentiable on the interval a, b, closed interval, then there exists a c for a is less than c less than b, such that we have f of b over f of a is equal to the multiplicative derivative of f at c to the power of b minus a. Right? Typically, if you wanted to translate it completely from to multiplicative arithmetic, we would have the to the power 1 over b minus a on the other side. But anyways, we could just raise it here to make it simpler instead of dealing with reciprocal exponents like that. Similarly, we also have these tests that I can show here on screen for basically conditions of increasing and decreasing intervals and extremum tests, right? These transfer over where instead of checking for the standard derivative to be 0, here we check the multiplicative derivative to be 1 instead, right? The unit multiplicative thing here, like for empty products or something, would be 1 instead of like empty sum, it's 0, right? So that is a nice extension. Within the talk of differential equations, certain standard ones can be turned into ones with multiplicative derivatives if you have any logarithmic derivative present. For example, if we have y prime is equal to y times some f of x, right? You can divide by the y, exponentiate both sides, and what we're going to get is the multiplicative derivative y star is equal to f of x. So then you know that y is going to be equal to c times the multiplicative integral from like 0 to x, right, of f of t dt, right? So we have this certain type of thing. You could also have other types of basically strictly multiplicative differential equations just with those operators and other combinations. So they are usually harder to solve, or you need to, again, build them based around multiplicative arithmetic to kind of get easier results. But yeah, along with this, many other things can be deduced in terms of multiplicative form, like Taylor's theorem as shown here. If you also know Abel's summation formula, you can find a form of Abel's multiplication formula where you have multiplicative integrals involved. And along with this, it also extends to multivariable calculus, right? You can find multiplicative, multivariable chain rules, stuff like that, or variational calculus, like maximizing multiplicative functionals, right? Now, a lot of this seems to just follow from basically using multiplicative arithmetic, right? Like a lot of things here seem to just follow from changing things, like, so if we have a multiplicative form of addition, it becomes this multiplication. The difference seems to become this ratio. Then we have power, or multiplication seems to become power, and then division seems to become the reciprocal power, right? So a lot of things in the formulas seem to follow just from switching up the arithmetic like this, which again sort of comes from the base of using logarithm and exponential rules to change them up like that. But it's pretty interesting to see how pretty much most of these formulas you could just think about it in the same way like this, like I'll just transfer these operations into this different way, and they normally do work out for a lot of these. In general, with this restricted set of functions with like basically positive functions, it might seem like this has a downside, but actually a lot of things, it's more helpful to think about them in a multiplicative way, right? Or in more realistic scenarios if we have positive functions here. Things like with economics or finance, Black-Scholes models, multiplicative thinking is more prevalent there, as well as within probability with like entropy, and this is that you have integrals of logs or sums of logs, right? You could even find a type of multiplicative law of large numbers where the geometric mean can approach this multiplicative integral like shown here. Now, taking on with this, we basically can have actually infinitely many non-Newtonian calculi. All we have to do is basically take some transformation here. I'll use phi, some transformation, and then apply it and its inverse separately with these other operations, right? If we have this in this phi calculus, the derivative here can be just transformed from the original one as phi of phi inverse composed with f prime of x, right? Or if we want this integral to be phi of the standard integral of phi inverse composed with f of x dx, right? And again, this would normally be, again, restricted under, I guess, the basis of these, the domain or the range of these transformations. Also, I'm pretty sure that normally they have to be injective, right? They have to be invertible in this standard way. But potentially you could make it work, although it might be a little bit more jank with things like sine and arcsine. But again, they aren't exactly properly invertible in the sense that you have all these different multiples or additions of angles 2 pi n, right, to make it work. And along with this, you could even do the same thing for any type of modified arithmetic, right? If we have some random operation, which I'll use like an O plus, right? Under this transformation, we can make it turn into this new form using phi of phi inverse of x with the operation on phi inverse of y, right? So this is really interesting, as this basically expands way further than just multiplicative calculus, though again I think this might be still more applied than some of the other hypothetical infinite calculi, but it's very interesting how much you can generalize this to these other abstract forms with abstract transformations. So I hope you enjoyed this video, and always stay curious, and I'll see you in the next one. Bye.